The footprints are still there, pressed into the grey dust on the surface of the moon, undisturbed, perfectly preserved. The same shallow impressions left by 12 human beings across 6 missions between 1969 and 1972. No wind has touched them. No rain has fallen. Nothing has moved them in over 50 years. On December 14, 1972, Gene Cernan climbed the ladder of the lunar module, sealed the hatch behind him, and became the last human being to stand on another world. Not a single person has been back since. The program that put him there consumed 4.5 cents of every dollar the United States federal government spent at its peak. It employed over 400,000 people. It produced the most powerful rocket ever flown. And then it stopped. 52 years of silence, not because we forgot, not because we failed, but for a reason far stranger than either. In July of 1969, Apollo 11 landed on the Sea of Tranquility and won the most expensive contest in the history of human civilization. That victory is the reason no one has been back. In this video, we will excavate what Apollo actually was, trace what was destroyed when it ended, and follow the long, complicated road that leads, slowly, imperfectly, back to the surface of the moon. If that sounds like your kind of thing, a like and a subscribe means more than you might think. The story begins not with a rocket, but with fear. What that fear built, and what it took with it when it left, is the whole of what follows. That fear has a precise origin. It has a date, a location, and a sound. But before we get there, we need to spend a moment with what was left behind. Because the story of why we have not gone back does not begin with a cancelled program, or a shrinking budget, or a shift in political will. It begins with something much simpler and much more uncomfortable. It begins with what Apollo actually was. Cast your mind back to December of 1972. The Apollo program has been running for the better part of a decade. 12 human beings have walked on the moon across 6 successful landing missions. They have planted flags, collected 842 pounds of rock and soil, deployed scientific instruments across the surface, and driven an electric rover across the grey dust. The final crew, Eugene Cernan, Harrison Schmitt, and Ronald Evans, have just completed the most scientifically ambitious lunar mission ever flown. Cernan is the last one up the ladder. He pauses at the bottom rung, takes one final look at the landscape around him, and speaks a few quiet words he had prepared for this moment. Then he climbs. The hatch seals, the ascent engine fires, and the human presence on the moon ends. It has not resumed since. Now here is the question most people never think to ask. Not why did we stop, but what exactly did we have when we stopped? What did 12 years of effort actually produce? What capability did humanity possess in December of 1972 that it could, in principle, have built upon? The common assumption is that Apollo left a foundation, that it proved the engineering worked, demonstrated the techniques, validated the hardware, and established a capability that sat waiting, dormant, available, for the moment when the will to return finally arrived. This assumption is the source of almost every misunderstanding about why we have not gone back. Apollo did not leave a foundation. Apollo was an event, a singular, self-contained, non-repeating event. And understanding why requires dismantling something that has been repeated so often. It has taken on the quality of established fact. The idea that going to the moon once means going back should be straightforward. It does not. Here is what Apollo actually proved. Under conditions of extraordinary political urgency, with a budget that consumed a larger share of federal spending than any peacetime program before or since, with a workforce of over 400,000 people mobilized across the entire industrial geography of the United States, with a tolerance for crew risk that would be considered unconscionable by modern standards, and with a deadline set not by engineering readiness, but by geopolitical necessity, it is possible to land small teams of extraordinarily brave people on the lunar surface for brief visits and bring most of them home alive. That is the achievement. It is magnificent. It is one of the supreme feats in the history of our species. But it is also a very specific thing, and it is a very different thing from what people generally imagine when they say we could simply go back. To understand why those conditions existed at all, you need to go further back, past the Saturn V and the lunar module and the mission control rooms and the astronaut corps. Back to the exact moment when the idea of going to the moon stopped being science fiction and became a matter of national survival. The night it changed was in October of 1957. You would not have heard anything remarkable if you had been standing outside that evening. No explosion, no visible streak across the sky, just a faint, steady radio signal if you happen to have the right equipment. A pulse repeating every 96 minutes, circling the planet above you. The Soviet Union had placed a metal sphere into orbit around the Earth. It weighed 83 kilograms. It was roughly the size of a beach ball. It carried no weapons, performed no meaningful science, and could do nothing except circle the planet and transmit that pulse. Sputnik. The name has since acquired a kind of nostalgic quality. The first satellite, a milestone of exploration, a symbol of the space age beginning. That is not how it felt in the United States in the autumn of 1957. It felt like the floor had dropped out from under a nation that had assumed, with deep and largely unexamined confidence, that it was the most technologically advanced society on Earth. Think about the specific fear that Sputnik triggered. This was not abstract anxiety about falling behind in a competition. This was the deep winter of the Cold War. Both superpowers were building nuclear arsenals at a pace that was genuinely terrifying to observe even from inside the process. The doctrine of mutually assured destruction had made nuclear war something that both sides spent enormous intellectual energy trying to prevent, because the alternative was the end of organized human life. And into this environment, the Soviet Union had just demonstrated something that reordered every military calculation on the planet. If they could place an object in orbit, any object, they could place a nuclear warhead anywhere on Earth. Sputnik was not a satellite. It was proof of concept for an intercontinental ballistic missile, dressed in the clothing of a peaceful scientific experiment. The reaction in the United States was not measured. Congressional hearings were convened within weeks. Newspapers ran front-page editorials comparing the event to Pearl Harbor. Parents wrote letters to their elected representatives, asking whether their children were safe under a sky now patrolled, at least in part, by Soviet technology. School science curricula were overhauled almost overnight. A national crisis of confidence erupted that reached into every layer of American society. And then it got worse. On April 12, 1961, a 27-year-old Soviet Air Force pilot named Yuri Gagarin climbed into a spherical spacecraft called Vostok 1, launched from a remote site in the Kazakh steppe, completed a single orbit of the Earth in 108 minutes, and returned safely. The United States had not yet placed a human being in orbit. The man who had designed the rocket that carried him was known publicly only as the chief designer. His name was Sergei Korolev, and it was a state secret. The Soviets understood that his genius was a strategic asset that Western intelligence services would attempt to neutralize if they could identify him. So the most consequential rocket engineer of the 20th century operated in official anonymity, his identity protected by the same apparatus that had imprisoned him in a Siberian labor camp 2 decades earlier. Across the developing world, the nations still choosing sides in the Cold War, weighing their futures against the competing claims of capitalism and communism. The message of Gagarin's flight was clear and devastating. The Soviet system works. It produces results. The future may belong to Moscow. This was the environment in which a young American president, less than 4 months into his first term, looked at his available options and landed on the moon. John Kennedy was not a space enthusiast. His private correspondence, examined across decades of careful research by the historian John Logsdon, reveals a man almost entirely uninterested in space as a domain of scientific inquiry. What Kennedy understood, with sharp political intelligence, was prestige. He understood leverage. He understood that the United States was losing a contest for global influence and needed a stage large enough and unambiguous enough to reverse the narrative. The moon provided that stage. Nothing else available to him, no military program, no economic initiative, no diplomatic maneuver, could produce a single undeniable demonstration of technological supremacy visible to every nation on Earth simultaneously. The moon was the largest possible canvas for the message he needed to send. On May 25, 1961, Kennedy addressed a joint session of Congress. The speech is remembered today as one of the great declarations of human ambition. What is less often remembered is the 3 weeks that preceded it. The Bay of Pigs invasion had failed catastrophically. Gagarin had just completed his orbit. Kennedy had met with Nikita Khrushchev in Vienna and come away shaken by what he had encountered. The speech was not delivered from a position of strength. It was delivered from a position of genuine alarm. He said the nation should commit itself to achieving the goal, before the decade was out, of landing a man on the moon and returning him safely to the Earth. Those words are usually quoted as though they were spoken in a spirit of soaring aspiration. Consider them instead in the context of everything that preceded them. A failed invasion. A Soviet space program running ahead of anything America could match. A geopolitical contest that felt to the people living inside it like it could be lost. Kennedy was not interested in the moon. He was interested in not losing the Cold War. The moon was the instrument. The distinction matters enormously, because it is the distinction that explains everything that came next. To turn that commitment into reality required something that had no precedent in American peacetime history. The budget allocation that followed Kennedy's speech moved at a speed the modern legislative process cannot replicate. At its peak in 1966, NASA consumed approximately 4.5% of the entire United States federal budget. Hold that figure for a moment. 4.5 cents of every dollar the federal government spent on a single agency, pursuing a single objective. Expressed in the terms of today's economy, that figure represents something in the range of $150 billion per year. NASA's entire annual budget today sits at approximately $25 billion, representing less than half of 1% of federal spending. Apollo-era NASA received roughly 6 times more funding in real terms than the agency receives now. And that funding did not arrive slowly, through years of incremental negotiations and committee deliberations. It arrived fast, with a political consensus that reflected the urgency behind it. Over 400,000 people worked on Apollo at the program's height. Not 400,000 NASA employees, 400,000 people across approximately 20,000 companies, universities, and government facilities spread across every state in the Union. The supply chain was a portrait of a nation's industrial capacity redirected toward a single purpose. The Grumman Aircraft Engineering Corporation on Long Island built the Lunar Module. North American Aviation in California built the Command and Service Module. Boeing in New Orleans assembled the first stage of the Saturn V. Douglas Aircraft in Huntington Beach built the third stage. IBM produced the guidance computers. Each organization was itself a network of subcontractors and suppliers spreading outward in every direction. The work culture inside this machine was unlike anything that had existed in peacetime. 70 and 80-hour weeks were standard. Engineers slept at their desks. Families went months without seeing a parent who had effectively taken up residence inside a facility. Test failures that today would trigger years of review were examined, corrected, and cleared in a matter of weeks. The schedule pressure was not incidental to the program, it was structural. Kennedy's deadline was not aspirational. It was operational. Every design trade, every material choice, every manufacturing decision was measured against the end-of-decade clock. This is not simply a story about money or manpower, though both were extraordinary. It is a story about what happens when a society suspends its normal institutional restraints because it has decided, at the level of genuine existential fear, that the cost of failure is higher than the cost of almost anything else. The man who translated that urgency into program architecture was George Mueller, the NASA official appointed to oversee Apollo's day-to-day operations from 1963 onward. Mueller had come from the defense sector, where managing complex systems under military pressure was simply the job. He arrived at the agency and immediately concluded that its cautious, incremental testing approach, fly each component separately before ever integrating the whole, would not survive contact with Kennedy's deadline. So he scrapped it. He mandated what became known as all-up testing, fly the complete rocket stack, fully integrated from the very first launch. His own colleagues thought he had lost his mind. He was right. The approach worked, and it is a significant part of why Apollo landed on the moon in 1969 and not 1973. But Mueller's approach only worked because the environment permitted it. In a program operating under normal institutional constraints, the risk embedded in all-up testing would have been politically impossible to accept. In Apollo, it was not just acceptable, it was necessary. Because the political cost of missing the deadline exceeded, in the minds of the people making these decisions, the political cost of a catastrophic test failure. That inversion, where the cost of not trying is perceived as greater than the cost of losing people, is what created the program. It is also what makes the program, in the deepest sense, unrepeatable. Not because the engineering cannot be done again. It can. But because the conditions that generated the will, the budget, the mobilization, and the risk tolerance belong to a specific historical moment. A moment defined by the particular terror of the early Cold War, by the specific alignment of superpower rivalry and nuclear anxiety and demographic momentum and cultural unity around a national objective. That moment is over, and the program it produced ended with it. The window, in other words, was already closing before the first Saturn V ever left the ground. What happened when it finally shut is where the real story begins. What that window produced, before it closed, was the most extraordinary piece of machinery in the history of human engineering. To appreciate what Apollo actually built, and what was lost when it ended, you need to stand next to it. Not in a photograph, not in a documentary frame, but as close as your imagination will allow. The Saturn V stood 363 feet tall, taller than the Statue of Liberty, including her pedestal. It weighed roughly 3,000 tons fully fueled. Its first stage alone housed 5 engines produced by Rocketdyne, each one generating 1.5 million pounds of thrust. Together, they produced 7.5 million pounds of force at ignition, enough to lift the entire vehicle, plus its crew and payload, off the ground and accelerate it towards space. At full throttle, those 5 engines consumed 15 tons of kerosene and liquid oxygen every single second. Think about what 15 tons per second means. From the moment the engines lit to the moment the first stage separated, roughly 2.5 minutes later, the Saturn V burned through more propellant than a fully loaded passenger aircraft weighs. It did this while carrying a crew of 3 human beings toward the moon. The vehicle could deliver approximately 130 metric tons to low Earth orbit. Roughly 50 metric tons could be sent on a trajectory toward the moon. It remains, more than half a century later, the most capable launch vehicle ever successfully flown. Nothing built since, not the Space Shuttle, not the Falcon Heavy, not the Space Launch System that carries Artemis crews today, has matched its raw payload capacity to the moon. We have not built its equal. In some respects, we have not even come close, and each one flew exactly once. Every Saturn V was expendable. The entire vehicle, from the enormous first stage to the instrument unit at the top, was used for a single mission and then discarded. The first stage fell into the Atlantic Ocean. The second stage followed it. The third stage was either sent into solar orbit or deliberately crashed into the moon. Only the command module, a cone roughly 3.5 meters wide, returned to Earth. The rest was gone. Wernher von Braun, who had spent his career building progressively larger rockets, and who had driven the Saturn V's development from his office at the Marshall Space Flight Center in Huntsville, Alabama, understood better than anyone what the vehicle represented. He also understood what its expendability revealed about the program's underlying purpose. This was not a transportation system. It was a delivery mechanism for a single political objective. It was built to be used and thrown away because nobody, not the engineers, not the administrators, not the politicians, seriously expected it to be needed more than a dozen times. 13 Saturn V's were flown across the program. Each one cost approximately $1.5 billion in today's money. The total hardware expenditure on launch vehicles alone was staggering, and every gram of it was designed around one goal: reach the surface and come back. Nowhere was this philosophy expressed more precisely than in the vehicle that actually landed. The lunar module was built by Grumman Aircraft Engineering Corporation on Long Island, and it remains one of the most extreme examples of engineering optimization ever produced. Every design decision was made in the service of one requirement: reduce mass. Every kilogram removed from the vehicle was a kilogram that the ascent stage did not need to lift off the lunar surface. Every gram saved on the descent stage was a gram that could be reallocated to propellant or scientific equipment or crew consumables. The consequences of this philosophy were structural. In certain sections of the cabin, the pressure vessel walls measured approximately 1/3 of a millimeter thick, thin enough that a technician pressing too hard with a tool during assembly risked puncturing the hull. The crew cabin contained the bare minimum of everything. The seats were removed entirely to save weight. The astronauts stood at their positions during the descent. The instrument panels were stripped to essentials. The windows were small rectangles, precisely the size required for the tasks they needed to serve, and no larger. But none of these details carry the weight of a single design decision made about the ascent engine. When the crew was ready to leave the moon, a single engine fired. One. There was no backup, no redundant propulsion system, no secondary ignition source, no alternative means of getting off the surface if the primary engine failed to light. The ascent engine had to work the first time, every time, with no second chance available. If it did not fire, the crew would die on the moon. That was not a remote contingency buried in a risk register. It was a plainly acknowledged outcome that the program accepted and moved past. The engineers who designed the ascent engine knew this. The astronauts who flew it knew it. Richard Nixon's speechwriter William Safire knew it well enough to draft a contingency statement for the president to read in the event it happened. A prepared eulogy addressed to the widows of Neil Armstrong and Buzz Aldrin, titled simply, "In Event of Moon Disaster." The speech was written. It was kept ready. Nixon never needed it. Here is what that tells you about Apollo, that no photograph or documentary can quite convey. This was a program willing to build a vehicle with a single point of failure on the most critical maneuver of the entire mission. Not because the engineers were reckless, they were among the most careful human beings who ever lived, but because the alternative was adding mass, and adding mass meant compromising the mission, and compromising the mission was the one thing that could not be permitted. The architecture was ruthlessly, single-mindedly optimized for one objective: get there, perform the surface activities, get back. The entire machine, the 3 million part assembly that was the Saturn V and its payload, existed to serve that sequence of events and nothing else. It was not designed to be repeated indefinitely. It was not designed to support a permanent presence. It was not designed to enable the kind of sustained operations that a lunar outpost would require. It was designed to win a race that had already been decided by a speech in 1961. Understanding this is the beginning of understanding why returning to the moon has taken so long. The machine Apollo built was extraordinary. It was also entirely unsuited to the purpose that would eventually be required of any serious return. The men who flew inside it understood the risks with a clarity that is difficult to fully appreciate from the outside. Internal analyses conducted within NASA during the Apollo program estimated the probability of crew loss on any individual mission at somewhere between 1 in 20 and 1 in 10, depending on the mission phase under consideration. On some specific phases, ascent from the lunar surface, translunar injection, lunar orbit insertion, the assessed risk was higher still. The cumulative probability across the full program that at least one crew would be lost was considered substantial by the people doing the mathematics. they proceeded anyway. The astronauts themselves were almost uniformly former military test pilots, and the culture of test flight in the 1950s and 60s had a particular relationship with mortality that is not easy to describe without sounding clinical. These were men who had spent their professional lives strapping into aircraft that had a meaningful chance of killing them. They had attended the funerals of colleagues who had not made it back. They had developed, through years of immersion in that environment, a psychological orientation toward risk that amounted to a professional philosophy. Not recklessness exactly, but a deeply internalized acceptance that the work required placing yourself in situations where survival was not guaranteed, and that this was inseparable from doing the work at all. Several Apollo astronauts later described their relationship with danger in terms that, applied to a modern crew selection process, would trigger immediate psychological review. This was not a flaw in the program. It was a feature. The Cold War demanded it. And then, on the evening of April 13th, 1970, it almost ended. James Lovell, Jack Swigert, and Fred Haise were 56 hours into the Apollo 13 mission when an oxygen tank in the service module ruptured. The explosion vented the contents of one tank immediately and caused a slow leak in the second. Within hours, the command module had lost most of its oxygen and electrical power. The crew transferred to the lunar module, the descent vehicle that had been intended to carry two of them to the surface, and used it as a lifeboat for the return journey to Earth. What followed was 72 hours of improvised survival. The lunar module's carbon dioxide scrubbing system used round canisters of lithium hydroxide. The command module used square ones. The round canisters were running out. The square ones could not fit the round sockets. A team on the ground, working with exact replicas of the equipment available on board the spacecraft, devised a method of connecting the square canisters to the round sockets using materials already on the vehicle: plastic bags, cardboard, tape, a sock. The solution worked. The crew survived. Apollo 13 is often described as a successful failure, a mission that did not achieve its objectives but brought its crew home. What it actually demonstrated, in the starkest possible terms, was the degree to which the program was operating at the absolute margin of what human ingenuity and improvisation could sustain. One slightly different failure mode, a rupture earlier in the mission, a different set of available materials, a longer duration before the problem was identified, and 3 men would have died in deep space. The broader societal tolerance for outcomes like this existed because the Cold War had created a moral framework in which the cost of losing the space race was perceived as greater than the cost of losing astronauts. This was never stated openly in those terms, but it operated beneath the surface of every budget decision and every risk assessment and every launch approval throughout the program. It does not operate that way anymore. On January 28, 1986, the Space Shuttle Challenger broke apart 73 seconds after launch. All 7 crew members were killed. The shuttle fleet was grounded for 32 months. A presidential commission investigated every dimension of what had happened: the physical cause, the decision-making process, the institutional culture that had allowed a known risk to be managed downward until it killed people. Then it happened again. On February 1st, 2003, the Space Shuttle Columbia disintegrated during re-entry. All 7 crew members were killed. The fleet was grounded again, this time for more than 2 years. The Columbia Accident Investigation Board produced a report that examined not only the physical failure, foam debris striking the leading edge of the orbiter's wing during launch, but the deeper institutional failure that had allowed the risk to be normalized. The board was direct about what it found. The organizational culture inside NASA had contributed to the accident as surely as the foam had. These responses were appropriate. They reflected a society that had decided, rightly, that human lives should not be spent casually in the pursuit of programmatic objectives. But they also demonstrate something important about the world in which any future deep space program must operate. A single crew loss today would not merely delay a program. It would almost certainly halt human deep space exploration for a generation. Congressional investigations would stretch across years. Public confidence would collapse. The institutional momentum required to sustain a long-duration program would be broken in ways that might prove impossible to repair within any politically relevant time frame. Apollo operated in a narrow historical window in which political urgency inverted the normal relationship between risk and institutional self-preservation. Challenger and Columbia closed that window permanently. What this means for everything that came after is not a counsel of despair. Modern programs are right to be cautious. Human lives matter, and a program that treats them as expendable is not a program worth running. But it does mean that the pace, the risk tolerance, and the sheer institutional momentum that characterized Apollo are simply not available to any successor. The tools that built the footprints are gone, and the conditions that made those tools possible are gone with them. What happened when the last mission landed, and what the world did with the capability it had spent a decade and billions of dollars building, is where the story turns genuinely dark. On July 20th, 1969, Neil Armstrong stepped off the bottom rung of the lunar module's ladder and placed his left foot onto the surface of the moon. The political objective of the entire Apollo program was achieved in that instant. Not when the crew returned safely. Not when the rocks were analyzed. Not when the mission was declared a complete success by every metric available. The objective was achieved the moment a human being of American nationality stood on the lunar surface before a Soviet cosmonaut did. The race had a finish line, and the finish line had just been crossed. Everything that followed, 5 more successful landing missions, hundreds of hours of surface activity, 842 pounds of return samples, the deployment of scientific instruments that continued transmitting data for years, was conducted against a backdrop of rapidly dissolving political will. The purpose that had generated the program had been served. The urgency that had suspended normal institutional constraints was bleeding away with every passing month. The Soviet Union never landed cosmonauts on the moon. Their program, driven by Sergei Korolev until his death during routine surgery in January of 1966, and struggling thereafter without his singular engineering genius, suffered a series of catastrophic failures with the N-1 rocket that would have been their equivalent of the Saturn V. All 4 N-1 test flights ended in disaster. The program was quietly cancelled in 1976, and the Soviet Union did not publicly acknowledge its existence for another 13 years. The race had been lost by the only other competitor. The field was empty. And in the absence of a competitor, the argument for continuing became progressively harder to make. Richard Nixon, who had inherited the program from Lyndon Johnson and who faced the fiscal pressures of the Vietnam War alongside a restive domestic political landscape, was not unsympathetic to NASA's aspirations. But he was a political realist, and the political reality was unambiguous. NASA Administrator Thomas Paine, who had overseen the Apollo 11 landing and who genuinely believed the agency could sustain its momentum into a program of permanent space stations and eventual Mars missions within decades, found his budget requests cut with a regularity that made long-term planning essentially fictional. Paine resigned in September of 1970, less than 14 months after the first moon landing, frustrated by an administration that had no intention of maintaining Apollo-era spending on space exploration. The congressional arithmetic was equally stark. Legislators who had been among the earliest critics of Apollo's cost, questioning whether the American taxpayers' money was well spent on lunar geology while cities burned and the war dragged on, were no longer an isolated minority. The question being asked in committee rooms across Capitol Hill was no longer whether the program was technically impressive. It was whether there was any compelling reason to keep paying for it now that it had achieved its stated goal. For a sufficient majority, the answer was no. Apollo missions 18, 19, and 20 were cancelled. The hardware for these missions was not hypothetical. Saturn V rockets were in various stages of production. Lunar modules were partially assembled. Astronaut crews had been named and were in training. The missions existed as real, executable programs. They were cancelled not because the engineering had revealed a problem, or because the missions were technically impossible, but because Congress declined to appropriate the money to fly them. This is perhaps the single most telling detail in the entire story. The United States possessed functional hardware capable of sending human beings to the moon and chose, through an ordinary legislative process, not to use it. The capability was real. The will was gone. The budget trajectory that followed was swift. NASA's share of federal spending, which had stood at approximately 4.5% in 1966, fell to roughly 1.5% by 1970 and continued declining through the decade. Television ratings for the later Apollo missions dropped sharply from the extraordinary figures recorded for Apollo 11. By the time of Apollo 17 in December of 1972, coverage had become almost routine, a remarkable inversion for a program that had, just 3 years earlier, stopped the world. The Vietnam War consumed the fiscal oxygen that might otherwise have sustained a serious post-Apollo program. The social upheavals of the late 1960s had redirected political attention toward urgent domestic concerns: healthcare, urban poverty, education. The competing claims on federal resources were real and legitimate, and they were being advanced by constituencies with genuine political power. Space exploration, magnificent as it was, had no comparable domestic constituency once the Cold War rationale was gone. The engineers and contractors who depended on NASA funding were geographically concentrated and politically limited in their reach. The broader public, which had been transfixed by the first landing, moved on with the speed that democratic attention typically moves, to the next crisis, the next election, the next immediate concern. Here, then, is the argument stated as plainly as it deserves to be stated. Apollo did not end because it failed. It ended because it succeeded. Because the specific political objective that had justified its extraordinary resources, demonstrating American technological supremacy before the Soviet Union could claim that ground, was achieved so completely and so definitively that the program became instantly redundant the moment it worked. Apollo was not a foundation for sustained lunar exploration. It was a bridge built entirely from political urgency, and that bridge was dismantled from behind as each mission crossed it. By the time Cernan sealed the hatch in December of 1972, the bridge was already gone. The capability that had delivered 12 people to the moon across 6 missions did not sit waiting in a hangar somewhere, available to be reactivated when the political moment arrived again. It had already begun to dissolve, and how completely it dissolved is what most people find genuinely shocking when they encounter the details for the first time. There is a version of events in which what happened after Apollo was a sensible reordering of priorities. A mature space agency, having demonstrated the capability to reach the moon, turns its attention to developing infrastructure for a longer-term program. The hardware is carefully preserved. The workforce is retained in reduced form. The knowledge is documented and transmitted to the next generation of engineers. The capability hibernates, ready to be restored. This is not what happened. What happened was a demolition. The Saturn V production lines were shut down, not mothballed, shut down. The specialized tooling that had been purpose-built to manufacture components that existed nowhere else in the world, the massive jigs that held fuel tank sections in alignment during welding, the precision fixtures that positioned turbopump components for machining, the calibration rigs that validated guidance system performance, was disassembled. Some of it was scrapped, some was repurposed. None of it was preserved in a form that could be returned to production. The factories that had manufactured the Rocketdyne F1 engines were retooled. The machinery was redirected to other contracts. The production lines that had taken years to develop and refine were reconfigured for purposes that had nothing to do with deep space propulsion. The Michoud assembly facility in New Orleans, where the enormous first-stage fuel tanks had been welded together in a building so large it generates its own internal weather on humid Louisiana afternoons, did not stand empty. It was repurposed for Space Shuttle external tank production. The building existed. The overhead cranes existed. Some of the workforce remained, but the facility's purpose had been completely transformed, and the specific expertise that had accumulated there over a decade of Saturn V production the welding procedures calibrated to aluminium-copper alloys at cryogenic temperatures, the inspection protocols refined through hundreds of qualification tests, did not transfer cleanly to the new program. 3 Saturn V rockets survived. One lies on its side at the Kennedy Space Center in Florida. A second is displayed at the Johnson Space Center in Houston. A third stands at the U.S. Space and Rocket Center in Huntsville, Alabama. They are extraordinary objects, staggering in scale, moving in their history. But they are museum exhibits. You cannot fuel a display piece. You cannot launch an artifact. And a single rocket is not a space program in any case. A space program is a living system. Factories, supply chains, engineering teams, test facilities, launch infrastructure, and institutional knowledge functioning as an integrated whole. The rockets in those museums are organs removed from a body that no longer exists. The body cannot be reconstructed by preserving the organs. What was lost in the years following Apollo extended far beyond hardware, and the hardware loss alone was already catastrophic. The workforce, those 400,000 people whose collective expertise had made the program possible, dispersed within 5 years of the final lunar mission. These were not interchangeable workers performing generic industrial tasks. They were specialists of a kind that had never existed before and has not been assembled since. Welders who understood the specific metallurgical behavior of aluminium alloys used in cryogenic fuel tanks at temperatures approaching -250 degrees Celsius. Machinists capable of holding tolerances measured in 10,000ths of an inch on turbopump components, spinning at 6,000 revolutions per minute. Electrical engineers who had designed wiring harnesses containing miles of conductor, routed through environments of violent vibration and extreme thermal cycling. Systems engineers who understood how 10,000 subsystems from 200 different suppliers integrated into a single vehicle that had to function without failure on the first attempt, with human lives depending on every connection. When Apollo ended, these people did not wait. They found work. The welders went to shipyards and petrochemical plants. The machinists moved into automotive and defense manufacturing. The electrical engineers joined the nascent computer industry, which in the early 1970s was hungry for exactly the kind of precision thinking that spacecraft wiring required. The systems engineers dispersed across a dozen sectors where their ability to manage complexity was valued, even if never again applied to anything of Apollo's scale. Within 5 years, the collective expertise that had made it possible to land human beings on the moon was scattered across the American economy. Within a decade, much of it was effectively irretrievable. The masters had left. The apprentices who might have carried the knowledge forward had never been trained, because there was no program to train them for. The chains of transmission that keep specialized knowledge alive across generations had been broken. What remained was documentation, blueprints, technical reports, test data archived on magnetic tape and microfilm, thousands of pages of specifications and procedures and manufacturing instructions, stored in filing cabinets and warehouses across the country. What remained was not enough. The discovery of exactly how insufficient it was would not come for another 20 years, arriving at precisely the moment when the question of returning to the moon was beginning, slowly, imperfectly, and with little sense of what had actually been lost, to be asked again. In the 1990s, engineers at the Marshall Space Flight Center in Huntsville began pulling Saturn V documentation from the archives. A new generation of heavy lift concepts was being studied, and the natural starting point seemed obvious. The most capable launch vehicle ever flown had been built 30 years earlier, right here, by people who had worked in these same buildings. The drawings existed. The technical reports existed. The specifications ran to thousands of pages. Surely the foundation for a new program was sitting in those filing cabinets, waiting to be retrieved. What they found was something considerably more unsettling. The blueprints were incomplete, not missing exactly, but full of gaps that made them far less useful than expected. Manufacturing specifications referenced internal procedure codes that had no surviving key, designations that had been perfectly legible to the technicians of 1966, and were perfectly opaque to anyone reading them 30 years later. Assembly instructions contained phrases like, "per standard shop practice," at precisely the moments where the most critical details should have been specified. The standard shop practice was gone. It had walked out the door with the people who practiced it. This is the deeper meaning of what was lost when the Apollo workforce dispersed. Not the knowledge that propulsion physics works, or that aluminium can be formed into fuel tanks, or that guidance computers can navigate a trajectory to the moon. That knowledge exists in textbooks and in the training of every aerospace engineer alive. What was lost was something more specific and more practically devastating. The industrial capability to produce the specific hardware, refined through years of trial, error, and accumulated correction, carried not in documents, but in the hands and judgments of the people who had done it. Consider the F1 injector plate as a concrete example of what this means. The injector plate sat at the top of each F1 combustion chamber and was responsible for one of the most technically demanding tasks in the entire engine, introducing liquid oxygen and kerosene into the chamber in precisely the right spray pattern to sustain stable combustion at pressures approaching 1,000 pounds per square inch. The plate contained approximately 2,600 individual orifices, each precision drilled to a specific geometry. The positioning, the sizing, the angle of each hole relative to its neighbors, all of it had been worked out through years of test firings, each one revealing instabilities and asymmetries that were corrected in the next iteration. The final design worked. It worked consistently and reliably across every Saturn V that flew. But the knowledge of why it worked, which specific combinations of orifice geometry and spacing had proved stable, which had produced catastrophic combustion resonance, which marginal cases were tolerable and which were not, existed as tacit knowledge. It lived in the engineering judgments of the people who had run those tests, watched those failures, and made those corrections. It was not fully captured in any document, because full capture was not the purpose of the documentation. The documentation described the final design. It did not reconstruct the path to it. When engineers in more recent decades attempted to recreate F1 manufacturing using modern computer-controlled machining, the geometry was achievable. A modern CNC milling machine can drill 2,600 orifices to tighter tolerances than anything available in the 1960s. That part of the problem was not the problem. The problem was everything surrounding the geometry. The process parameters for the machining operations, speeds, feeds, toolpaths, work holding approaches, had to be developed from scratch. The validation criteria for the finished plate, which dimensional deviations were acceptable, which inspection results indicated a plate that would behave well in firing, which patterns in the test data suggested emerging instability, had to be reconstructed through expensive and time-consuming empirical work. You hear the phrase sometimes, offered as a kind of shorthand for this entire situation. We lost the technology. It is not quite accurate, and the inaccuracy matters. The physics of rocket propulsion did not change. The underlying engineering principles that govern combustion chamber design are as well understood today as they were in 1969. What was lost was not knowledge in the abstract. What was lost was the specific industrial capability to produce specific hardware, the supply chains that delivered exotic alloys in the required grades and quantities, the manufacturing processes refined through iterations of failure and correction, the quality control procedures calibrated to the unique demands of human-rated spaceflight hardware, and above all, the institutional reflexes that allowed experienced people to make the 1,000 small judgments per day that a complex production program requires. Rebuilding this capability is not a matter of pulling old drawings from a filing cabinet and handing them to a modern machine shop. It requires reconstituting an entire ecosystem of specialized production, and doing so in an industrial environment that has been transformed beyond recognition since the 1960s. Supply chains have globalized. Manufacturing facilities have been consolidated, retooled, or closed. The specialist subcontractors who once supplied unique components to the Saturn V program have been absorbed, restructured, or simply ceased to exist. The RS-25 engine, which burns at the heart of the Space Launch System that now carries Artemis crews, is a direct descendant of the Space Shuttle main engine. Aerojet Rocketdyne has manufactured these engines over decades, and the accumulated production knowledge represents exactly the kind of institutional capability that was destroyed when the Saturn V program ended. Rebuilding the RS-25 production line after a gap between shuttle retirement and Artemis development required significant investment, years of effort, and the relearning of processes that had lapsed even across a gap of only a few years. It was an object lesson in miniature of the Saturn V problem, a preview of what happens when specialized capability is allowed to go dormant, even briefly, even with far better documentation than existed in the 1970s. Multiply that challenge across the 3 million individual parts of a Saturn V, and you begin to understand the scale of what was surrendered when the program ended without a successor. What was destroyed was not a set of blueprints. It was a living system of knowledge and capability that had taken a decade and a national mobilization to build, and that was allowed to dissolve in 5 years for want of a political reason to keep it together. Into the space left by that dissolution, a new program arrived. It was sold to Congress and the American public with promises that, in retrospect, were always going to be difficult to keep. The Space Shuttle was proposed in the early 1970s as a revolution in space transportation. The pitch was straightforward and seductive. A fully reusable spacecraft that would launch like a rocket, operate in orbit like a laboratory, and land like an aircraft. Flight rates of 40 to 50 missions per year. Per-flight costs reduced so dramatically that access to space would become almost routine. A vehicle so versatile that it could serve military, scientific, and commercial customers simultaneously, rendering the expensive expendable rockets of the Apollo era obsolete and paying for itself through the breadth of its utility. NASA Administrator James Fletcher championed the program through the political negotiations of the early 1970s, with an argument that was as much economic as it was technical. The shuttle would make spaceflight affordable. It would open a new era. It would ensure that the investment of the Apollo years was not simply abandoned. Almost none of the promises materialized. The shuttle flew 135 missions across 30 years of operations. That is an average of approximately 4.5 flights per year, not 50. The turnaround time between flights stretched to months, not the weeks originally projected. The vehicle required an enormous standing army of technicians to inspect, refurbish, and recertify after every mission, because each flight exposed the orbiter to thermal and mechanical stresses that demanded verification before the next. Reusability, which was supposed to reduce costs by eliminating the need to build a new vehicle for each mission, instead drove costs up by imposing a maintenance burden that nobody had fully anticipated in the design phase. When all operational and infrastructure costs were included, the standing workforce, the launch facilities, the processing infrastructure, the contractor support, each shuttle mission cost approximately $1.5 billion, not the fraction of Apollo costs that had been promised, not meaningfully less than an expendable vehicle would have cost for the same payload, roughly the same, and there was a ceiling that no amount of operational improvement could have raised. The shuttle's maximum operational altitude was approximately 600 kilometers. The moon is 384,000 kilometers away. The shuttle could no more reach the moon than a harbor ferry could cross an ocean. Yet for 30 years, this vehicle consumed the overwhelming majority of NASA's human spaceflight budget, workforce, facilities, engineering attention, and institutional focus. Every dollar spent operating the shuttle was a dollar not spent developing the next generation of deep space transportation. Every engineer assigned to shuttle processing was an engineer not working on the technologies that any serious return to the moon would require. Think about what those 30 years actually prevented. Closed-loop life support systems capable of sustaining crews for weeks or months beyond low Earth orbit received only modest laboratory research funding, nowhere near the sustained investment needed to produce flight-ready hardware. Lunar lander designs remained on paper. advanced radiation shielding for deep space environments progressed through conceptual studies, but never reached the prototype stage. In situ resource utilization, the technology that could eventually allow crews to extract water and produce propellant from the lunar surface, existed as a theoretical framework discussed at academic conferences, not as engineering hardware being developed toward operational use. Deep space habitation modules, next-generation spacesuits designed for the abrasive lunar terrain, autonomous surface power systems, each represented a decade-long development challenge that received intermittent study funding, producing reports and recommendations, but no flight hardware. The International Space Station deepened this pattern. Its first module launched in 1998, and the construction campaign that followed consumed enormous resources across more than a decade. The station is a genuine marvel, a testament to international engineering cooperation on a scale without precedent, and a platform for scientific research in the near-weightless environment of low Earth orbit that has produced invaluable data. Long-duration microgravity studies conducted aboard the station have generated insights into human physiology that will be essential for any future deep space mission. That work matters, but the station exists in low Earth orbit. Its highest point is approximately 400 kilometers above the Earth's surface. The Moon is nearly 1,000 times further away. And like the shuttle that built it, the station absorbed budget, engineering capacity, and institutional attention that might otherwise have been directed toward the technologies that would actually be needed when humanity finally tried, seriously, to go back. For 30 years, the combined effect of shuttle operations and station construction kept NASA's human spaceflight program in an orbit that, by the standards of what Apollo had achieved, was barely off the ground. What happened when the shuttle finally retired, and what 3 decades of deferred development actually meant for the programs that followed, is where the full weight of those choices becomes clear. There is a structural problem at the heart of every post-Apollo attempt to return to the Moon, and it has nothing to do with engineering. The engineers, given sufficient time and resources, can solve the technical challenges. They always have. The problem is the relationship between the timescale that deep space development requires and the timescale that democratic governance provides. Here is the arithmetic, stated plainly. Developing a human-rated deep space transportation system from initial concept to operational flight takes somewhere between 10 and 15 years under favorable conditions. This is not a pessimistic estimate or a bureaucratic excuse. It is the observed historical reality across multiple programs in multiple countries. The Space Shuttle took approximately 9 years from formal program approval to its first flight. The International Space Station took over a decade from initial agreement to the launch of its first module. The Space Launch System, building substantially on heritage hardware from the shuttle program, took more than 12 years from formal authorization to its first flight. The Orion capsule has been in continuous development for the better part of 2 decades. These timelines are not failures of execution, though inefficiency has contributed to most of them. They reflect the genuine complexity of designing, building, testing, and certifying systems that must function with extreme reliability in environments that destroy most human-made objects. Human spaceflight hardware must survive launch vibration severe enough to shake apart conventional structures. It must operate in hard vacuum. It must manage thermal extremes spanning hundreds of degrees. It must protect crew members against radiation and micrometeorites over operational lifetimes measured in years. Certifying that hardware meets these requirements involves testing campaigns that cannot be meaningfully compressed without accepting risks that no sensible person would accept. Now consider the political timeline against which this technical timeline must operate. An American president serves a maximum of 8 years. Congressional terms run 2 years for the House and 6 for the Senate. Federal budgets are authorized and appropriated annually, with limited mechanisms for binding future Congresses to multi-year commitments. Each new administration arrives with its own space policy priorities, its own appointed NASA administrator, its own relationship with congressional committees, and its own calculation about how to allocate discretionary spending in a budget environment where every dollar has competing claims. The arithmetic is unforgiving. A program requiring 25 years of sustained investment must survive at least 3 and possibly 4 changes of presidential administration. It must maintain support across 6 or 7 congressional election cycles. It must weather economic recessions, geopolitical disruptions, competing domestic priorities, and the inevitable technical setbacks that accompany any complex development effort. It must do all of this while producing visible progress at a pace fast enough to justify continued investment, but slow enough to be technically responsible. No post-Apollo lunar program has survived this gauntlet. On July 20th, 1989, the 20th anniversary of the Apollo 11 landing, George H.W. Bush stood on the steps of the National Air and Space Museum in Washington and announced the Space Exploration Initiative. He called for a return to the Moon and eventual human missions to Mars. The announcement was made with genuine intent. NASA was asked to study what it would take. The resulting document, known as the 90-Day Report, outlined an architecture that would require an estimated $500 billion over 20 to 30 years. Congress recoiled. The initiative was functionally dead within 2 years, not because the goal was technically impossible, not because the engineering analysis was flawed, because the price tag, stated honestly, was more than the political system was willing to contemplate. 15 years passed. In January of 2004, George W. Bush announced the vision for space exploration. The shuttle would be completed and retired. A new crew vehicle would be developed. Astronauts would return to the Moon by 2020, using the Moon as a stepping stone toward Mars. The resulting program was named Constellation, and it was the most concrete attempt at lunar return since Apollo itself. Michael Griffin, the NASA administrator who inherited the program and drove its early development with genuine engineering rigor, oversaw the design of 4 major elements. The Ares 1 rocket would carry the crew capsule to orbit. The Ares 5 heavy lift vehicle would carry the lunar lander and departure stage. The Orion capsule would carry astronauts to and from the Moon. The Altair lander would carry them to the surface. Real engineering work was performed across all 4 programs. Metal was cut. Tests were conducted. Hardware was built and tested. The people working on Constellation were not shuffling paper. They were making genuine progress toward a real objective. But the program was chronically underfunded relative to its ambitions from the beginning. Each annual budget cycle delivered less than the program needed to maintain its schedule. Delays compounded. Costs grew. The gap between what Constellation required and what the political system was willing to provide widened steadily through the mid-2000s. In 2009, the incoming Obama administration commissioned a review of NASA's human spaceflight plans. The committee, chaired by Norman Augustine and composed of respected figures from across the aerospace and policy communities, spent months examining Constellation's status with care and rigor. Its conclusion was precise and damning. The program's goals were not executable within projected budget profiles. Without significant budget increases that neither the administration nor Congress was prepared to provide, Constellation could not achieve a lunar landing within any realistic timeframe. In 2010, Constellation was cancelled. The Ares 1 and Altair lander were terminated. Billions of dollars in development work was archived rather than flown. Charles Bolden, the NASA administrator who oversaw the cancellation, faced the task of redirecting an agency that had spent 6 years building toward one goal and now had to rebuild around another. The human cost of this decision extended far beyond wasted budgets, and it is worth pausing on it for a moment. Engineers who had relocated their families to Huntsville or Houston or the Cape for the promise of building the next generation of deep space vehicles found themselves reassigned to programs with uncertain futures or laid off entirely. Specialists who had spent 5 or 6 years developing expertise in Constellation-specific systems, the Altair lander's throttled descent engine, the Ares 5 Earth departure stage, the surface habitat thermal protection architecture, found that their skills had no immediate application elsewhere. Some moved into the commercial sector, which was beginning its own rapid development at precisely this moment. Others left aerospace entirely, taking with them the kind of deep space engineering experience that would be desperately needed when the next lunar program appeared. This is the accumulated damage of the start-stop cycle, and it compounds with each iteration. Every cancellation does not merely fail to advance the goal, it actively sets back the effort by dispersing teams, wasting invested capital, and eroding the institutional confidence that any future program will survive long enough to reach completion. Engineers who joined NASA or its contractors in the early 2000s to work on Constellation watched it cancelled. Some of those same engineers were subsequently assigned to the Space Launch System and Orion development. Younger colleagues entering the field today have no institutional memory of a time when a deep space human exploration program ran to completion. Their entire professional experience has been shaped by programs that started, struggled, and stopped. What this does to a workforce over time is profound and largely invisible. It breeds a specific kind of caution, a reluctance to invest fully in any program's long-term vision, because experience has taught that the vision will change with the next administration. It makes recruitment harder because the most honest answer to the question of whether any given program will still exist in 10 years is an uncomfortable silence. It disperses expertise at the precise moments when it should be accumulating. Rockets can be designed on paper relatively quickly. Factories can be built in a few years. But developing a workforce with the skills, the experience, and the institutional confidence to execute a program as complex as sustained lunar presence takes a generation. That generation must be recruited, trained, and retained, not just long enough to design hardware, but long enough to see it built, launched, and operated. The start-stop cycle denies them that continuity, and in doing so, it undermines the foundation on which any future program depends. But here is the counterexample that makes this story more complicated than simple institutional failure. Since November 2nd of the year 2000, human beings have occupied the International Space Station without interruption. More than 25 years of continuous habitation across 5 American presidential administrations, multiple changes of government in every partner nation, 2 major economic crises, the loss of the Space Shuttle Columbia, and the retirement of the shuttle program entirely. The station survived all of it. How? The answer is instructive because it describes precisely what every post-Apollo lunar program lacked. The first mechanism was international dependency. The station was not an American project that other nations participated in. It was a genuinely multinational infrastructure in which each partner contributed hardware on the critical path. The European Space Agency built the Columbus Laboratory Module and the Automated Transfer Vehicle. The Japan Aerospace Exploration Agency built the Kaibo Laboratory, the largest single module on the station. The Canadian Space Agency built the robotic arm systems, without which the station could not have been assembled. Roscosmos provided Soyuz vehicles for crew transportation during periods when no American option was available. This distribution of responsibility meant that cancelling the station was not simply a domestic budget decision. It would have required the United States to walk away from legal and diplomatic commitments to allies whose cooperation was needed across dozens of other policy domains. The cost of cancellation extended far beyond the space program into the broader fabric of international relationships. No administration was willing to pay that cost. The second mechanism was domestic economic distribution. Station components were manufactured in facilities spread across multiple states. Operations were managed from centers in Texas, Florida, and Alabama. The program employed thousands of people in communities where aerospace work represented a significant fraction of the local economy. The political constituency for the station's continuation was not confined to space enthusiasts. It was embedded in the electoral interests of representatives from states that depended on those jobs. The third mechanism was continuous visibility. Crews launched regularly. Science results were published. Astronauts became public figures who maintained genuine connections with ordinary citizens through media coverage, educational outreach, and in more recent years, through social media. The station was never out of the public eye long enough for its existence to become abstract or forgettable. Artemis has been deliberately structured to replicate these mechanisms, and this is one of the most important and least discussed aspects of the current program. The Artemis Accords, which establish shared principles for lunar exploration and have been signed by over 40 nations, create diplomatic expectations that raise the cost of American withdrawal. The European Space Agency builds the service module for the Orion capsule, the section that provides propulsion, power, and life support during the transit to and from the Moon. This is not a symbolic contribution. Without the European service module, Orion cannot fly. The Japan Aerospace Exploration Agency is developing a pressurized lunar rover. The Canadian Space Agency is contributing robotic systems for the Gateway. Each contribution creates a mutual dependency that binds partner nations to the program's continuation. The commercial dimension adds a layer of resilience that no previous lunar program has possessed. SpaceX is developing the Starship human landing system under a contract structure where NASA pays milestone-based fees while the company invests substantial private capital in the underlying vehicle development. Starship is not being built solely for NASA. It is being developed as a general-purpose transportation system with commercial satellite launch, private spaceflight, and eventually point-to-point Earth transport applications. The lunar landing mission is one use case among many. This means that even if the specific NASA program were disrupted by a future budget cycle or a change in administration, the fundamental vehicle development would likely continue, because SpaceX has independent commercial motivation to complete it, regardless of government lunar policy. This decoupling of technology development from single administration political cycles is genuinely new. It did not exist during Constellation. It did not exist during any previous post-Apollo program. Whether it is sufficient to break the cycle that has defeated every previous attempt is a question the coming decade will answer. But to understand whether any of this is enough, you first need to understand what the engineering actually demands. Because the political challenge is only half the story. The other half is the Moon itself, and what it takes to survive there for longer than 3 days. The Moon itself has not changed. That is worth saying plainly before anything else. The surface that Gene Cernan left in December of 1972 is the same surface that a future crew will land on. The distance from Earth is the same. The gravity is the same. The regolith, the craters, the silence, unchanged. What has changed is everything we require of the mission. Apollo asked one question of every system aboard its spacecraft. Can you keep 2 people alive for 3 days on the lunar surface and get them home? That question, brutal in its simplicity, shaped every design decision across the program. The lunar module's open-loop life support was perfectly suited to answering it. Oxygen was stored in high-pressure tanks and released into the cabin as the crew breathed it. Carbon dioxide exhaled by the astronauts was scrubbed from the cabin air by passing it through canisters packed with lithium hydroxide, a chemical that absorbs carbon dioxide through an irreversible reaction. When a canister was saturated, it was swapped for a fresh one. Water was generated as a byproduct of the hydrogen-oxygen fuel cells that produced electrical power. Food was pre-packaged. Waste was collected and stored. This system was elegant in exactly the way a disposable thing can be elegant. It was simple, well understood, and required no recycling, no regeneration, and no maintenance beyond swapping spent canisters for fresh ones. For a 2-person crew over 3 days, the consumable mass was manageable. The numbers worked. Now change the mission parameters and watch the numbers fail. A 4-person crew for 28 days requires roughly 19 times the oxygen, 19 times the lithium hydroxide capacity, and proportionally more water than Apollo's surface stays demanded. The total consumable mass for an extended lunar surface mission using open-loop systems would exceed the entire payload capacity of the lunar module by a margin that no amount of engineering optimization could close. You cannot carry enough supplies to sustain a crew for a month using systems designed for a 3-day camping trip. The architecture that worked brilliantly for Apollo fails completely when the mission duration is extended, not because the design was flawed, but because it was never intended to scale. The solution exists. It has been operating continuously in low Earth orbit for over 2 decades. The International Space Station's Environmental Control and Life Support System, developed and refined over years of operation, does not discard its consumables. It recycles them. The water recovery system processes moisture from cabin air, crew perspiration, and urine through a sequence of filtration, distillation, catalytic oxidation, and ion exchange processes, producing potable water that meets drinking standards. With the addition of the brine processor assembly, which extracts residual water from the concentrated waste stream, the system achieves water recovery efficiency of approximately 98%. The oxygen generation system electrolyses that recovered water, splitting it into hydrogen and oxygen, venting the hydrogen and routing the oxygen back into the cabin atmosphere. The carbon dioxide removal assembly uses regenerable molecular sieve beds that can be cycled thousands of times, absorbing carbon dioxide on one pass and releasing it to space on the next, rather than consuming a fresh chemical canister each time. The mass savings compared to open-loop systems are transformative. Instead of launching all the water a crew will consume across a month-long mission, you launch a modest initial supply and recover most of it continuously. Instead of carrying hundreds of lithium hydroxide canisters, you install a regenerable system that processes carbon dioxide indefinitely, with only periodic maintenance. But closed-loop life support introduces complexity that open-loop systems deliberately avoid, and that complexity carries consequences that matter enormously on the lunar surface. The water recovery system on the station is a sophisticated chemical engineering installation. It requires regular maintenance, replacement of filters, catalytic beds, and ion exchange resins at scheduled intervals. It has experienced failures during its operational life: pump seizing, contamination events disrupting the processing chemistry, sensor malfunctions requiring troubleshooting and repair. On the station, these failures are manageable. Resupply vehicles can deliver replacement components within weeks, and the crew can survive on stored reserves while repairs proceed. On the Moon, the calculus is different in kind, not just degree. A resupply delivery to the lunar surface requires a dedicated launch, a multi-day transit, a landing, and an unloading operation. The minimum time between identifying a failure and receiving replacement hardware is measured in weeks to months, not days. A spare parts inventory sufficient to cover likely failure modes must either be carried on the initial mission, adding mass, or manufactured locally using capabilities that do not yet exist at operational scale. The redundancy requirements for lunar life support are therefore substantially higher than for station operations, and higher redundancy means more hardware, more mass, more complexity, and more potential failure modes to manage. Beyond the redundancy challenge, adapting station-derived life support to the lunar surface introduces technical problems that the station's environment never presented. The station operates in microgravity. Many fluid processing systems rely on gravity-driven separation of phases, liquid from gas, concentrated solution from dilute, and these processes must be redesigned for the lunar surface, where gravity is 1/6 of Earth's, not zero, but not enough to drive fluid behavior in the same way terrestrial systems assume. Lunar regolith dust infiltrates virtually every mechanism it contacts, and the contamination risks to filters, fluid handling components, and precision seals are not trivial on a surface where every excursion coats equipment in abrasive, electrostatically charged particles. The thermal environment, which swings from over 100 degrees Celsius in sunlight to below -170 in shadow, imposes stresses on every material and seal that the station's carefully regulated orbital environment never experiences. None of these problems will stop a lunar program. They are engineering problems, and engineering problems yield to sustained effort and investment. But each one requires years of development work, component testing, system integration, and operational qualification before it can be trusted to keep people alive on a surface where the nearest rescue is 3 days away. The life support systems for sustained lunar presence represent not an incremental improvement on Apollo, but a fundamentally different technological generation, one more closely related to what will eventually be needed for Mars than to anything that flew in the 1960s. The gap is real, the investment required to close it is substantial, and the time that gap represents is measured not in months, but in years. Life support is the system that keeps you breathing. Radiation is the environment that will kill you slowly if the system succeeds. The Moon has no global magnetic field. Earth's magnetic field deflects most of the energetic particles that stream continuously through the solar system, creating a protective bubble within which the surface is largely shielded from the worst of space radiation. The Moon lies outside that bubble. It has no atmosphere worth mentioning. The surface pressure is roughly 10 trillion times lower than at sea level on Earth. Nothing stands between the lunar surface and the full, unfiltered spectrum of space radiation. There are two distinct threats, and they are different enough in character that each demands its own engineering response. The first is galactic cosmic rays. These are high-energy particles, primarily protons and heavier atomic nuclei, produced by supernovae, neutron star mergers, and other violent astrophysical processes throughout the galaxy. They arrive at the Moon continuously, from every direction simultaneously, at energies that are almost difficult to comprehend. Some individual galactic cosmic ray particles carry kinetic energies comparable to a professionally thrown baseball, concentrated into the nucleus of a single atom. They penetrate conventional shielding materials with relative ease, and in some configurations, they interact with shielding atoms to produce secondary cascades of particles that can increase the radiation dose behind thin shields rather than reducing it. Effective protection against galactic cosmic rays requires mass, substantial mass, either in the form of meters of regolith piled over habitat modules, or thick layers of hydrogen-rich materials such as polyethylene or water, which are more effective at absorbing and dissipating the secondary cascade. Galactic cosmic rays accumulate. The dose they deliver is roughly proportional to time spent on the surface, which means that a 30-day surface stay delivers approximately 10 times the galactic cosmic ray exposure of a 3-day stay. Over the course of multiple mission rotations, the accumulated dose begins to approach and potentially exceed career exposure limits established under modern spaceflight medical guidelines. The second threat operates on a completely different timescale. Solar particle events are intense bursts of energetic protons ejected by the Sun during coronal mass ejections and solar flares. Where galactic cosmic rays are a slow, continuous background, solar particle events are acute and sudden. A significant event can deliver in a matter of hours a radiation dose that would normally accumulate across months of background exposure. The warning time between the first observable signs of an event on the solar surface and the arrival of the energetic particle front at the Moon is sometimes as little as 15 to 30 minutes. The duration of the hazard can extend from hours to days. The August of 1972 offers the clearest illustration of what this means in practice. A major solar proton event occurred between the Apollo 16 and Apollo 17 missions, in the gap between two flights, when no crew was on the surface. The estimated radiation dose for an unshielded astronaut on the lunar surface during that event was several hundred millisieverts delivered over a matter of hours. That dose sits in the territory of acute radiation syndrome, nausea, fatigue, immune system suppression, and significantly elevated lifetime cancer risk. Whether it would have been lethal depends on the specific exposure geometry and the individual, but it would unquestionably have constituted a medical emergency with no treatment available and no rapid return to Earth possible. For a 3-day mission, accepting the solar particle event risk was a calculated gamble consistent with Apollo's overall approach. The probability of a major event coinciding with any specific 72-hour window is low. Across a small number of missions, the cumulative probability remains manageable if you are willing to accept the consequences if the gamble goes wrong. For missions lasting weeks, the calculation transforms entirely. The probability of encountering at least one significant solar particle event during an extended surface stay is not a minor risk factor. Across multiple mission rotations lasting a month each, it becomes close to a certainty over the program's lifetime. Sustained surface operations therefore require shielding infrastructure that Apollo never carried and never needed. Habitat modules, buried under several meters of regolith or sited within lava tubes that provide natural overhead coverage, can substantially reduce galactic cosmic ray exposure. Dedicated storm shelters within every pressurized volume, capable of providing meaningful protection during a solar particle event, and stocked with enough provisions for a crew to remain inside for 24 to 72 hours, are not optional features for a permanent outpost. They are non-negotiable requirements. Layered on top of all of this is the thermal environment, which Apollo navigated by the simple strategy of not staying long enough to confront it fully. The Moon rotates once every 29.5 Earth days. At most locations on the surface, this means approximately 14 days of continuous sunlight, followed by 14 days of continuous darkness. During the sunlit period, equatorial surface temperatures climb to roughly 120 degrees Celsius. During the lunar night, they plunge to approximately -170 degrees. The swing between the two extremes spans nearly 300 degrees Celsius, and because the Moon has no atmosphere to store or redistribute heat, the transition occurs relatively rapidly as the Terminator crosses the surface. Apollo missions landed during lunar morning at carefully selected equatorial sites, ensuring moderate and stable thermal conditions throughout the surface stay. The crews were never on the surface long enough for the thermal environment to shift significantly. The lunar module's thermal control system was designed for a narrow operating window and a short duration. It did not need to handle the full range of the lunar day-night cycle because it was never exposed to it. A sustained presence cannot choose its thermal window. Equipment must function at temperatures that would freeze carbon dioxide solid during the night and approach the boiling point of water during the day. Materials expand and contract through thermal cycles that stress joints, seals, and structural connections with every rotation. Electronics must either be kept warm during the lunar night through active heating, powered by a system that must itself function continuously, or designed to survive repeated deep thermal cycling without performance degradation. Lubricants in mechanical systems must remain functional across a temperature range that defeats every conventional lubricant chemistry. Each of these constraints is solvable, but each solution requires mass, power, and development time. And each sits on top of the life support challenge, and the radiation challenge, and all the others that follow, compounding, not adding, because a lunar outpost must address all of them simultaneously, not sequentially. The engineering gap between what Apollo required and what sustained presence demands is not a matter of degree. It is a difference in kind. Understanding that difference is what allows you to understand why the mission is taking as long as it is. There is an answer to the thermal problem. It does not come from engineering alone, it comes from geometry. The Moon's axial tilt, the angle between its rotational axis and the plane of its orbit around the Sun, is approximately 1.5 degrees. Earth's axial tilt is 23.5 degrees, which is what gives our planet its seasons, its variation, its rhythmic cycle of warmth and cold. The Moon, tilted by barely more than a degree, has almost none of that variation. The Sun never rises particularly high above the horizon at the poles, and it never sets far below it. At certain elevated locations near the lunar South Pole, the combination of the Moon's minimal tilt and local terrain geometry means the Sun never sets at all, or nearly never. These are the peaks of eternal light, ridges and crater rims near the South Pole that remain in near continuous sunlight as the Moon completes its orbit around the Sun. At the most favorable locations, illumination exceeds 90% of the lunar year. The 14-day night that makes an equatorial outpost so difficult to power never fully arrives. Solar arrays positioned on these peaks can generate electricity through what would otherwise be a killing darkness, sustained by a geometry that requires no technological breakthrough to exploit. Only the recognition that the right location changes everything. The lunar geologist Paul Spudis, who spent decades arguing that the polar regions were not merely scientifically interesting, but architecturally essential for any serious human return, was among the earliest researchers to map these illumination patterns systematically. His case was simple and ultimately persuasive. The question of where to build the first permanent lunar outpost is not primarily a question of scientific preference. It is a question of where the physics allows you to survive. But there is more to the South Pole than light. Immediately adjacent to those sunlit peaks, separated in some cases by distances of only a few kilometers, lie the permanently shadowed craters, regions of the lunar surface that have not seen direct sunlight in billions of years. The geometry that keeps the peaks in near-continuous light keeps the crater floors in perpetual darkness. Temperatures in these craters fall to approximately -230 degrees Celsius. That is colder than the surface of Pluto, colder than the cloud tops of Neptune. Among the coldest naturally occurring environments in the solar system. And into these craters, over geological timescales, something has been accumulating. Water ice, delivered over billions of years by cometary impacts and implanted by the solar wind as hydrogen ions, combined with oxygen in the regolith. Unable to sublimate in the absence of any sunlight, it has simply stayed. Locked in the cold, in the dark, in craters that have been sealed from the sun since before the first complex life appeared on Earth. The confirmation came on October 9th, 2009. The Lunar Crater Observation and Sensing Satellite, a small spacecraft deliberately impacted into the Cabeus crater near the South Pole, produced an ejector plume that was immediately analyzed by a following observation vehicle. The spectral signature was unambiguous. Anthony Colaprete and his team at NASA Ames Research Center published the finding in the journal Science the following year. Water ice was present in the shadowed craters of the lunar South Pole, in quantities sufficient to be scientifically significant and operationally relevant. The strategic importance of this discovery extends far beyond the value of water itself, though water on the lunar surface is transformative enough on its own terms. Consider what the presence of accessible ice actually means for the long-term economics of space exploration. Every kilogram of anything launched from Earth to the lunar surface costs an enormous amount of money. Propellant is the heaviest and most consumable component of any space mission, and the need to carry return propellant all the way from Earth to the Moon and back imposes a mass penalty that compounds brutally through the rocket equation. If propellant can instead be produced on the lunar surface, by extracting water ice, electrolyzing it into hydrogen and oxygen, and storing the resulting gases as cryogenic propellants, the economic character of deep space exploration changes in a fundamental way. The Moon ceases to be a destination that drains resources and becomes a supply depot that generates them. Missions departing from the lunar surface or refueling there during transit to deeper destinations could carry dramatically less propellant from Earth. The cost of accessing the inner solar system falls. The architecture of the entire human presence beyond Earth reorganizes around a local resource base rather than a terrestrial one. This is the vision that researchers like Spudis articulated for years before the water ice confirmation made it operational rather than speculative. The South Pole is not where Artemis is going because it is the most scenically dramatic location. It is where Artemis is going because, under current technology constraints, it may be the only location where a permanent human presence is physically viable. The extraction process itself is not simple. Mining equipment must function in permanent darkness at temperatures that defeat most conventional materials. Seals contract and become brittle. Lubricants freeze. Electronics must be actively heated to remain operational. The excavated regolith containing ice must be transported to processing facilities where it is gently heated, allowing the ice to sublimate directly from solid to vapor without passing through a liquid phase. The resulting water vapor is captured, condensed, purified, and either stored for crew use or routed to electrolysis systems that split it into hydrogen and oxygen. Those gases must then be liquefied and stored at cryogenic temperatures for use as propellant. Every step in this chain requires hardware that must work reliably, autonomously, and continuously in one of the most hostile environments available anywhere near Earth. None of it exists yet at operational scale. The technologies have been demonstrated in laboratories and in limited field tests. Robotic missions under NASA's Commercial Lunar Payload Services program are designed in part to characterize the ice deposits more precisely and validate extraction concepts before crews arrive. But the gap between laboratory demonstration and the operational resource production capacity that would make the South Pole genuinely self-sustaining is not a gap that closes in years. It is one that closes in decades through iterative deployment, testing, and refinement on the surface itself. The South Pole is the right destination. Getting there is only the beginning of what needs to happen there. The surface of the Moon is covered in a layer of material that spent billions of years being made as dangerous as possible. Micrometeorites have bombarded the lunar surface continuously throughout its history, each impact shattering the existing rock into smaller fragments and melting some of it into glass. Without wind, without water, without any of the erosive forces that round and smooth rock particles on Earth, these fragments have remained exactly as each impact created them: sharp, angular, jagged at every scale. The finest particles, a significant fraction of which measure only a few micrometers across, are essentially tiny shards of glass and mineral, and they carry persistent electrostatic charges acquired from solar ultraviolet radiation and the solar wind. These charges cause them to cling tenaciously to every surface they contact, including each other, and especially including the fibers and seals of equipment brought to the surface from Earth. The Apollo astronauts encountered this material during every surface excursion, and their accounts are consistent and illuminating. Regolith infiltrated spacesuit joints and degraded their mobility. It scratched helmet visors, reducing optical clarity. It coated thermal control surfaces and optical instruments, compromising their performance. It was tracked into the lunar module cabin on suits and equipment after each excursion, spreading through the interior and becoming increasingly difficult to manage. Harrison Schmitt, who served as the lunar module pilot on Apollo 17 and was the only professional geologist to walk on the Moon, reported experiencing symptoms after returning to the cabin that he described as resembling hay fever. Nasal congestion, irritation, a general discomfort that persisted for hours. The dust that caused it was not merely an inconvenience. It was a preview of a problem that becomes genuinely serious at the timescales that a permanent outpost would involve. For a 3-day mission, the dust effects were tolerable. Schmidt's symptoms resolved. The scratches on the visors were documented and accepted. The reduced thermal control performance was managed. None of it was mission critical. Extend the exposure to weeks and months and the picture changes. Abrasive regolith particles accelerate wear on mechanical seals and bearings in ways that compound continuously. Dust accumulation on solar array surfaces reduces power generation efficiency, a problem that, at an outpost where power is life-critical, cannot be ignored indefinitely. Contamination of filters and fluid handling components in the life support system degrades performance over time, increasing maintenance demands and reducing operational margins. Fine dust particles suspended in cabin air from repeated suit ingress, even with mitigation measures in place, represent an inhalation hazard that has no simple resolution. NASA's Human Research Program has assessed lunar dust as a genuine health risk for sustained surface operations. The concern is not acute toxicity, but chronic exposure. The nanoscale silicate particles in lunar regolith, the finest fraction of an already fine material, present a respiratory hazard profile that researchers have compared to the risk associated with terrestrial silicosis and asbestosis. These are conditions caused by prolonged inhalation of fine mineral particles, producing progressive and irreversible lung damage over years of exposure. The comparison is not precise because the lunar material is chemically distinct from the minerals associated with those diseases. But the physical mechanism, microscopic sharp particles lodging in lung tissue and causing inflammatory responses, is similar enough to demand serious attention. Mitigation is possible. Airlock designs that create a dust buffer zone between the exterior and the pressurized interior, reducing the amount of regolith that enters the habitable volume. Suit port systems that allow astronauts to enter and exit suits from the outside, without bringing the dust-covered exterior of the suit inside at all. Dust-resistant coatings applied to critical optical and thermal surfaces. Continuous filtration systems capable of removing fine particles from cabin air over months of operation. Each of these represents a genuine engineering solution that can meaningfully reduce the exposure, though none eliminates it entirely. And then there is the body itself. Radiation and dust address what the environment does to equipment. But the moon also does things to the human body that have nothing to do with what surrounds the outpost, and everything to do with the gravity, or rather the lack of it, inside. Lunar gravity is approximately 1/6 of Earth's. That is enough to keep you on the surface and to give fluid systems a preferred direction to settle. But it is not enough to maintain the physiological state the human body has spent hundreds of millions of years evolving to occupy. Long-duration spaceflight on the International Space Station has produced a detailed and sobering picture of what reduced gravity does to human physiology over months of exposure. Bone density decreases as the skeleton is relieved of the loading it was built to carry. Muscle mass declines, particularly in the postural muscles that spend their existence on Earth working against gravity. The cardiovascular system, which on Earth pumps blood upward against gravitational resistance, adapts to the absence of that resistance in ways that take time and effort to reverse upon return to full gravity. Vision changes have been documented in a significant proportion of long-duration station crew members, a condition called spaceflight-associated neuroocular syndrome, in which elevated intracranial fluid pressure gradually remodels the structure of the eye, sometimes causing lasting changes to visual acuity. The immune system is suppressed in microgravity in ways that are not fully understood, but are consistent enough across crew members to represent a genuine health concern for extended missions. Lunar gravity is not microgravity. Some of these effects may be less pronounced at 1/6 of Earth's gravitational pull than at the near-zero gravity of the station. Some may not differ meaningfully. The honest answer is that we do not yet have sufficient data on human physiology, specifically in lunar gravity, to know where the differences lie, because no human has spent more than 3 days in that environment. Establishing that data is one of the scientific priorities of the Artemis program, and the results will shape the medical protocols and mission durations of every subsequent mission. Layered on top of all of this is the psychological weight of operating in an environment where help is genuinely far away. The communication delay between the Moon and Earth is approximately 1¼ seconds each way, a noticeable pause in conversation, but not the minutes or tens of minutes that would characterize a Mars mission. Operational autonomy on the lunar surface is high but not absolute. A crew experiencing a serious medical event or a complex system failure can still consult with specialists on Earth in near real time. What they cannot do is be evacuated quickly. Return to Earth from the lunar surface requires a functioning ascent vehicle, a functioning transit spacecraft, and a 3-day journey. The crew that needs rescue must first survive until the rescue is possible. This places demands on the psychological resilience of crew selection and preparation that are qualitatively different from the station, where a crew member in genuine medical distress can be back on Earth within hours. Managing the particular stress of operating in an environment where the margin for serious failure is narrow and where the nearest help is measured in days rather than hours is not an insurmountable challenge. It is one that requires honest acknowledgement and deliberate preparation. When all of these threads are gathered together, life support, radiation, the thermal environment, dust, physiology, psychology, what emerges is not a list of problems to be solved in sequence. It is a portrait of a system that must address all of them simultaneously, continuously, and reliably over months, with no possibility of emergency resupply and no rapid return. This is what a permanent lunar outpost actually requires. Not just a vehicle that can reach the surface, but an architecture capable of sustaining human life in all the ways that Apollo never needed to consider, because Apollo was never trying to stay. The architecture being built to meet these requirements looks nothing like what got us to the Moon the first time, and it is worth understanding why. When you look at images of the Apollo hardware, the Saturn V on the launch pad, the lunar module standing in the grey dust, you are looking at a system that was optimized with extraordinary elegance for a specific and limited task. 3 astronauts to the moon, 2 to the surface for a few days, all 3 home safely. The entire machine, beautiful as it was, existed to answer that one question. Artemis is not answering that question. It is answering a different one. And a different question demands a different architecture. The Gateway is a small space station placed in a near rectilinear halo orbit around the Moon, a highly elliptical path that carries it close to the lunar surface at its nearest point and out to significant distances at its furthest, completing each orbit roughly once every week. Its purpose is not to replicate the Apollo command module waiting in lunar orbit while 2 astronauts descended to the surface. Its purpose is to persist, to remain in that orbit across multiple missions, accumulating the infrastructure and logistics capability that eliminates the need for every crew rotation to launch the full stack from Earth all over again. A crew arriving at the Gateway can board a lander already docked there, descend to the surface, return, and depart without the massive launch expenditure that Apollo required for every single mission. Redundancy, resupply, habitat volume, science facilities. The Gateway accumulates these over time in a way that no single mission can deliver. The European Space Agency is contributing modules to it. The Japan Aerospace Exploration Agency and the Canadian Space Agency are contributing hardware. The Gateway is, in miniature, an application of the same international dependency logic that kept the International Space Station alive through 2 decades of political turbulence. The human landing system that will carry crews from the Gateway to the surface is a vehicle of a completely different character from anything that flew during Apollo. SpaceX's Starship stands approximately 50 meters tall. The lunar module, with its landing gear deployed, stood approximately 6.5 meters. The mass difference is not incremental. It is an order of magnitude. Starship's payload capacity to the lunar surface could carry habitation equipment, scientific instruments, pressurized rovers, resource extraction hardware, and enough supplies to support surface stays measured in weeks rather than hours. Each landing could deliver real infrastructure, not just a crew and their immediate consumables. The logistics of lunar surface operations transform from the near weightless constraint of Apollo, where every gram was agonized over, to something closer to a genuine expedition with meaningful equipment delivered on each mission. But this scale carries a dependency that has no precedent in the history of human spaceflight. Starship cannot reach the lunar surface on a single launch from Earth. The vehicle's propellant requirements for a lunar mission far exceed what can be carried at launch. Before a Starship configured for lunar landing can depart for the Moon, it must receive multiple deliveries of cryogenic propellant, supercooled liquid oxygen and liquid methane, from tanker variants of the same vehicle launched separately to low Earth orbit. Current estimates suggest that each lunar mission may require somewhere between 6 and 16 of these tanker flights, depending on final vehicle performance and the rate at which propellant boils off during the refueling process. Orbital propellant transfer at this scale has never been demonstrated. The technical challenges are real. Cryogenic liquids boil continuously when exposed to the thermal environment of low Earth orbit, and managing the boil-off across multiple sequential tanker dockings requires either rapid transfer operations or active cooling systems of their own. Achieving reliable fluid transfer between 2 vehicles moving in formation in near-zero gravity involves fluid mechanics that behave differently from anything in terrestrial experience. Maintaining propellant quality across many sequential transfers introduces contamination and stratification risks that must be managed carefully. These are solvable engineering challenges. SpaceX is actively developing the techniques. Flight tests are accumulating, but the gap between demonstrated capability and the reliable human-rated operation needed for a crewed lunar mission represents a significant remaining development task, and its schedule is uncertain in ways that matter to the overall program timeline. Blue Origin has been selected to develop a second human landing system under a separate contract, providing a redundant path to the surface that hedges against single provider risk, and introduces the competitive pressure that drives development programs to move faster than monopolies do. Before any crew steps onto the lunar surface again, robotic missions are going first. The Commercial Lunar Payload Services program is dispatching a series of commercial landers carrying instruments designed to characterize the South Pole environment in detail, mapping the ice deposits, measuring the radiation environment at ground level, testing mobility systems in the actual terrain, validating communications infrastructure. Each one closes a specific gap in the knowledge base that a crewed mission will depend on. The data they return will shape the design of the hardware that follows them. The Artemis architecture is more complex than Apollo. It involves more vehicles, more partners, more dependencies, more development threads that must converge before a crew can land. This complexity is not a bureaucratic failure. It is the honest engineering response to a problem that is genuinely more complex than Apollo's. You cannot establish a permanent outpost with 3 vehicles optimized for a 3-day visit. The architecture that the mission requires is the architecture being built. Whether the political will and the industrial momentum can sustain that architecture to completion is the question that everything else depends on. All of which brings us to a question that would have seemed almost theoretical a decade ago, but that now shapes every budget negotiation and every launch schedule and every diplomatic conversation in the space agencies of the world's most powerful nations. What happens if we are not the only ones going back? China's space program spent the better part of 2 decades being underestimated by Western observers. That period is over. The China National Space Administration has executed a sequence of lunar missions that, assessed without sentiment, represents one of the most impressive records of consistent achievement in the history of robotic space exploration. In December of 2013, the Chang'e 3 mission placed the first spacecraft to soft land on the Moon since the Soviet Luna 24 in 1976. In January of 2019, Chang'e 4 accomplished something no mission from any nation had ever done. It landed on the lunar far side, the hemisphere permanently facing away from Earth, unreachable by direct radio communication, requiring a relay satellite positioned above the lunar horizon to maintain contact. The mission was not a demonstration. It was a first, and it was executed flawlessly. In December of 2020, Chang'e 5 landed near the Mons Rumka volcanic formation, drilled into the surface, collected 1.5 kilograms of lunar material, and returned it to Earth. It was the first lunar sample return mission in 44 years. These are not the achievements of a program feeling its way tentatively into space. They are the achievements of an organization that has developed genuine technical competence, executed complex missions reliably, and is now applying that competence to goals of substantially greater ambition. China has announced plans for a crewed lunar landing targeting approximately 2030 to be enabled by the Long March 10 heavy lift rocket currently in development. Alongside Russia, China has announced the International Lunar Research Station, a planned permanent surface outpost intended to begin with robotic construction infrastructure in the late 2000s and progress toward crewed operations in the decade that follows. The program operates under its own governance framework, separate from and in explicit tension with the Artemis Accords that the United States and its partners have signed. Here is why this matters in ways that go beyond national prestige. The most strategically valuable real estate on the Moon is concentrated in a narrow band near the lunar South Pole. The permanently shadowed craters that hold water ice, the elevated terrain that receives near-continuous sunlight, the sites where surface power generation and resource extraction are both viable. These locations are not uniformly distributed across the surface. They are clustered. The number of genuinely optimal sites for a permanent resource-producing outpost may be limited. 2 programs both targeting the South Pole, operating under different legal frameworks, with different views on how resource use and operational zones should be governed, will eventually have to answer questions that the current international framework was not designed to resolve. The Outer Space Treaty of 1967, which all major spacefaring nations have ratified, prohibits national sovereignty claims over celestial bodies. No nation can plant a flag on the Moon and declare the surrounding territory its own. This principle is broadly accepted and unlikely to be challenged directly. But the treaty does not explicitly address what happens when a nation or a company extracts resources from the lunar surface, when they mine the ice, process it into propellant, and use it. Does that constitute appropriation of the body itself, which is prohibited? Or is it more like fishing in international waters, extracting value from a shared commons without claiming ownership of the commons? The Artemis Accords attempt to establish that resource extraction is consistent with the treaty and to build norms around transparency and the avoidance of operational conflicts. China and Russia have declined to sign. Their International Lunar Research Station proceeds under a separate framework that does not incorporate the Accord's principles. The potential for overlapping operational zones in a resource-rich polar region between programs operating under incompatible legal interpretations is not hypothetical. It is a foreseeable consequence of the current trajectory. The competitive dynamic that all of this creates has been valuable for Artemis. Bipartisan congressional support for the program has been strengthened explicitly and repeatedly by the recognition that the United States faces a credible competitor in cislunar space for the first time since the Soviet era. Funding that might otherwise have been vulnerable to the normal pressures of budget competition has been partially protected by the argument that falling behind China in space carries strategic consequences. The geopolitical dimension has supplied a motivating force that purely scientific or economic arguments have historically failed to generate. But this dynamic carries a risk that should be named clearly. If lunar return becomes framed primarily as a race, a contest to reach the South Pole before China does, to claim the resource advantage before the competitor arrives, then the resulting program faces exactly the pressures that made Apollo magnificent and unsustainable simultaneously. Compressed schedules, elevated risk tolerance, an architecture optimized for the single achievement of getting there first, rather than the infrastructure required to stay. A crash program designed to beat China to the South Pole by 2028 would look, in its essential structure, very much like Apollo. It would burn hot, it would produce a result, and it would struggle to sustain itself once the competitive objective was achieved. The most strategically sound outcome is the opposite. Arriving at the moon second, with an architecture genuinely designed for permanence, with habitats that last, power systems that function through the lunar night, resource extraction that reduces dependence on Earth, and crew rotations that accumulate rather than exhaust capability, is more valuable, over any time frame longer than a single political cycle, than arriving first with a program that cannot be sustained. Leaders who understand this difference are the ones who can turn the competitive pressure into a durable program rather than another sprint. Whether sufficient numbers of them exist across the administrations and congressional sessions that lie ahead is a question that cannot be answered yet. At the end of all of this, the primary barrier between humanity and a permanent presence on the moon is not technical. Say that again, because it runs against the way the problem is usually framed. The primary barrier is not technical. Engineers know how to approach the thermal problem, the South Pole, the peaks of near-continuous sunlight, the shielded habitats buried under regolith. They know how to approach the radiation problem, storm shelters, mass shielding, solar event monitoring networks. They know how to approach the life support problem, closed-loop systems derived from 2 decades of station operations, adapted to the specific demands of 1/6 gravity and lunar dust. They know how to approach the power problem, fission surface power systems, solar arrays on polar peaks, battery storage for brief shadow periods. They know how to approach the dust problem, suit port systems, sealed airlocks, continuous filtration. They know how to approach the resource problem, the LCROSS conformation of South Pole water. Ice provides a target, and the extraction pathway from ice to propellant is understood in principle, even where it has not been demonstrated at operational scale. None of these problems require a breakthrough in fundamental physics. None require the discovery of a new principle. All of them require sustained investment in development, testing, integration, and operational qualification. Given sufficient time and stable resources, engineers will solve every one of them. That is what engineers do. That has always been what engineers do. The problem that engineering cannot solve is the one that has ended every post-Apollo lunar program. The problem of sustaining political commitment across the timescale that the mission actually requires. A realistic timeline for establishing mature, self-sustaining lunar surface operations. Not a single visit, not a flag planted and a sample collected, but a working outpost with rotating crews and functional resource production. Spans 20 to 30 years from program initiation. This is not pessimism. It is the observed historical pace of every comparable infrastructure program ever attempted. The Transcontinental Railroad took decades of sustained investment through multiple presidencies, economic panics, and fierce political opposition. The Panama Canal required a federal commitment that persisted through engineering catastrophes, epidemic disease, and the failure of the private enterprise that attempted it first. The interstate highway system was funded consistently across administrations of both parties over more than 30 years, sustained not by visionary leadership, but by the prosaic recognition that the program delivered tangible benefits to constituents in every district. Each of these programs had something in common with a lunar outpost. Each required a form of commitment that extended far beyond any individual political cycle. Each demanded patience from institutions that are structurally oriented toward the short term. But each also had something that a lunar program does not. Each had a payoff that was legible to ordinary voters within a politically relevant time frame. The Transcontinental Railroad generated commerce that people could see. The canal reduced shipping costs that businesses could measure. The highways moved goods and people and connected communities in ways that were visible and immediate. The payoff from a permanent lunar presence, the long-term scientific knowledge, the eventual resource independence, the strategic positioning in cislunar space, and the foundational capability for eventual deep solar system exploration, is measured not in years, but in decades, and possibly in generations. The people who vote on the next appropriations bill will not personally receive most of the benefit. The people who receive the benefit will not vote for a long time yet. This is the deepest version of the challenge, not the engineering, not even the politics in the ordinary sense, but the question of whether a democratic society can sustain commitment to an objective whose return on investment is paid out across a time frame that exceeds the attention span of any individual electoral cycle. Artemis has better structural resilience against this challenge than any previous post-Apollo program. The international dependencies are real. The commercial decoupling is genuine. The diplomatic stakes are higher than they have ever been. The competitive pressure from China has supplied a motivating force that previous programs lacked. None of this guarantees survival through the political transitions ahead. But it changes the odds in ways that matter. What it cannot do is substitute for the commitment itself. The structural features are scaffolding. The building still requires someone to keep laying bricks across the years when no one is particularly watching, when the program is not producing headlines, when the budget is under pressure and the next election is close and the argument for cutting the space line feels easier than the argument for defending it. That is the work. It is not glamorous work. It does not produce the kind of moment that stops the world and holds 3 billion people in front of their televisions. But it is the work that the mission requires, and it has no substitute. Gene Cernan's footprints are still there, pressed into the grey dust of the Taurus Littrow Valley, undisturbed, unchanged, exactly as he left them on December 14th, 1972. They will still be there in 100 years, in 1,000. The moon preserves what is left on it with a patience that makes human timescales seem like a brief flicker. What those footprints represent has shifted across the decades since they were made. For a long time, they were symbols of achievement, evidence of what human beings could do when the stakes were high enough and the resources were sufficient and the will was present in full. That reading is not wrong. Apollo was an achievement of genuine and lasting magnificence. The courage of the men who flew those missions, the ingenuity of the engineers who built the hardware, the collective effort of 400,000 people who gave years of their lives to a goal that was audacious even by the standards of an audacious era. None of that diminishes in the light of what came after. But there is another way to read those footprints, and it is the reading that this entire story has been building toward. They are also the evidence of a specific kind of failure, not the failure of Apollo, which succeeded completely at what it set out to do, but the failure of everything that followed to understand what Apollo actually was. The failure to recognize that a program built on crisis cannot be sustained by inertia. The failure to preserve the capability that had been built at such extraordinary cost. The failure to replace political urgency with something more durable before the urgency dissolved. The half-century absence from the lunar surface is not a mystery. It is the entirely predictable consequence of a program that was designed for a sprint, succeeded at a sprint, and was then expected to become a marathon without anyone changing its shoes. What the current era offers, for the first time since 1972, is a genuine argument that the conditions for something more durable are assembling. Not perfectly, not quickly, not without the persistent risk that the next political transition will do what every previous political transition has done. But the commercial investment is real and motivated by something other than government contracts. The international commitments are real and carry diplomatic costs if abandoned. The competitive pressure is real and is supplying the political motivation that purely scientific arguments have never managed to generate. The technology development, slow and expensive and frustrating as it is, has survived long enough to begin accumulating momentum. The first Artemis crew to land on the moon, whenever that day arrives, will not be completing a mission in the way that Apollo 11 completed a mission. They will be beginning one. The years and decades that follow that landing will determine whether it becomes another glorious dead end, another footprint preserved in dust while the capability to return dissolves behind it, or the opening step of something that endures. That is a question no engineer can answer. No rocket can resolve it. No mission architecture, however clever, can guarantee it. It depends on steadiness, on the quiet, unglamorous, politically difficult work of maintaining commitment across the years when the drama has faded and the budget is tight and the finish line is nowhere in sight. It depends on whether enough people in enough institutions across enough nations understand, at a deep enough level, that what is being built is not a program, it is a foundation. And foundations take time. Apollo proved that human beings can be bold enough to do something extraordinary when the circumstances demand it. The 50 years that followed proved that boldness, by itself, is not enough. The moon is 3 days away. It has always been 3 days away. What stands between humanity and a permanent presence there is not distance, and it is not engineering, and it has never really been either of those things. It is the decision to keep going, even when the crisis that started it has long since passed. Whether we are capable of that decision, sustained across decades, through all the competing pressures of ordinary democratic life, is the only question that has ever truly mattered. And it remains, as it has always remained, entirely open.